We're going to begin learning about thermochemical equations, and I'm going to see if I can give you your last math lesson in chemistry. Let's go ahead and remember those common errors in calorimetry and how we could avoid them. Pause the video and think about it. So, welcome back. The purity of the samples could be fixed, maybe, if we refined the material perhaps or got a better sample. And the heat loss to the surroundings can actually be accounted for somewhat using graphical analysis. I'll show you how to do that in IB chemistry. Now, these assumptions are assumptions. Now, you will always have assumptions in every experiment. So that's going to be a tough sell to fix. So moving on into the heat of reaction. Remember that enthalpy is heat, right? It has a symbol H for heat. And the delta H means the change in enthalpy. So, and if delta H is negative, then the reaction is exothermic. If delta H is positive, then the reaction is endothermic. So an exothermic reaction. Well, it can be plotted here where we have the potential energy on the y-axis and reaction progress or time on the x-axis. And we'll get into these profiles later, but here we have the reactants here and the products here. So we can see that the products are lower on the position or have lower energy than the reactants, right? Because the heat has come out of it. So this little arrow right here is the activation energy, and this arrow is the enthalpy. Now the enthalpy, this change in enthalpy, right? This change from here to here, it went down. So since it went down, it is negative. That's why we have a negative for an exothermic reaction. Now exothermic reactions feel hot. We can use those in our hand warmers, or your body is doing exothermic reactions all the time. That's where you get your body heat, right? So in their exothermic reactions have the energy is released, they feel hot, they have a negative delta H, the energy of the reactants is greater than the products, and the heat is written as a product. Okay, now here's what I mean by that. So there are two ways to write it in a chemical equation. You can write it in the first line, you can either write it off to the side with the negative over here, and where the delta H equals negative whatever, and you just write it off to the side. Or you can include it into the equation itself, like I've done here, and it will be on the right side. You have a choice. You could put it on the left side or the right side. Well, for an exothermic reaction, it will show up on the right side. But be careful of that little guy right there. This positive right here, this does not mean that it has a positive enthalpy. It just means that you are adding it to the products. Okay, so a lot of students get those confused. You're not flipping signs or anything. You are just looking at it in a different way. Endothermic reactions are just the opposite. So the reactants are here and the products are here. So the activation is still this hump right here. We'll talk about this activation energy in a later video. And the reactants go to the products, and since it increased, it has a positive delta H. Endothermic reactions feel cold, kind of like your cold pack or your air conditioner, that Freon in your air conditioner, or baking soda and vinegar. That's an endothermic reaction. Lots of good ones. So energy is absorbed, and it feels cold, and has a positive delta H, and the energy of the products is greater than the reactants, and then heat is written as a reactant. So if it's written off to the side, you put a positive sign there. You please put that positive sign there. In this case, it really helps. I know in math, it's stupid to write a positive number. You don't need to, but when you're talking about thermochemistry, it's very helpful. Or please put it on the left side of the equation. All right, so exothermic was on the right, endothermic is on the left. All right, so a challenge question. Is an ice cube melting an endothermic or exothermic reaction? Pause the video and really think about this one. Well, did you say an endothermic reaction? Well, I hope you did. If you said exothermic, I see where you're getting it from because it's getting hotter, right? It should be exothermic. Well, that's not really what you should think about. You have to think about it in this way. Think about the system and think about the surroundings, all right? And then think about where the heat is going. The heat is going from the surroundings to the system, all right? And since it's going into the system, that's going to be an endothermic reaction. Always, 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 all right? Exothermic goes the other way. So let's follow up and see if you could do this one. Is water evaporation an endothermic or exothermic reaction? It's also going to be endothermic. So if you have your skin right here and you have your sweat, right? And let's just call the sweat your system, right? And then the beating sun is going to be the surroundings. The heat goes into that sweat and evaporates it. And as it evaporates it, it's an endothermic reaction. Therefore, it cools your skin off, right? So that's why we sweat. That's why so your sweat cools you off, all right? Cool. So now we're going to jump into the math portion. I'm going to make this as painless as possible. Each reaction will have its own unique little enthalpy change, all right? And those are tables that can be looked up. Now we can use this to predict how much energy will be evolved based on how much of the reactant we have or how much product is produced, all right? And yay, stoichiometry, hooray. So follow along in example 9 in your notes. I will post them in Schoology so you can see them. How much energy would be released if 500 grams of water is formed? We have the water production right here. Hydrogen plus oxygen makes water, and the delta H is negative 483.6 kilojoules per mole. So we'll start with 500 grams of oxygen, of water, I apologize. And grams aren't useful, so we'll convert them into moles. And then we are going to convert moles into kilojoules. All right, very cool. And that will bring us up to here. And that will tell us how much heat will be released. And we'll go ahead and round that answer. So you're probably scratching your head right now. Wait, Mr. Russell, we've always put 1 mole right here. Why are we doing 2? Well, check it out. So this number comes from here, right? That's the enthalpy of this reaction. Now this is kilojoules per mole. You can kind of think of it as kilojoules per reaction, right? That's how many kilojoules per this reaction. So this 2 comes from right here, all right? It comes from the coefficient of water, right? Here's water, and here's the 2. So that's where it comes from, and that's the math you should use. So let's try another one. We have propane, C3H8, plus oxygen yields CO2 and water. I'm not going to do the coefficients. Delta H is going to be negative 2,219.2 kilojoules per mole. If 5,000 kilojoules are released, what volume of oxygen would be consumed at STP? So we're going to do the same thing, but backwards this time. We're going to start with our energy, 5,000 kilojoules, and we're going to multiply by our kilojoules per mole right here. This is kilojoules and this is moles. So we're basically using it as another conversion factor. And then we are going to take that moles of O2 and we can convert moles of O2 into liters of O2, right? And we remember that there's 22.4 liters of O2 in 1 mole at STP, right? Remember our gases unit? And then that equals negative 252.3 liters. Excellent. So does that make sense? Does negative liters make sense? No, of course not, Mr. Russell. What you forgot to do is you forgot to put that negative there because it says that kilojoules was released. All right, so in these thermochemistry questions, always ask yourself at the very end, does this negative sign make sense? Does this answer make sense? All right, because you need to make sure you're watching out where this comes from. These negatives will sneak in there and mess up your calculations. Once again, that 5 came from here, and this number came from here. All right, last question, I believe. 14.4 grams of magnesium is burned in excess nitrogen at constant atmospheric pressure to form Mg3N2. 136.7 kilojoules of heat is given off. What is the molar enthalpy of formation, aka the molar enthalpy, of Mg3N2? Well, so let's just start with what we know. The molar enthalpy is going to be the enthalpy per mole, right? That's that kilojoules per mole thing I've been giving you. So the 14.4 grams of magnesium, well, let's just go ahead and turn it to moles. That seems like a logical step. Should by now. And well, let's find out how many moles of magnesium that is. All right. Now remember that the molar enthalpy of formation, this delta H, and sometimes you see an F there. Don't panic if you do. The units are kilojoules per mole. So all I'm going to do is going to take this kilojoules that I see right here and divide by my moles. All right. And then I'll hit the, and then I'll type in the calculator, and that's exactly what I get. That is the molar enthalpy of Mg3N2. Now, is it going to be negative or positive? It's going to be negative, okay? Now, how do we know that? What's that given, what's that key word? Magnesium is burned in excess nitrogen at constant atmospheric pressure. And then this kilojoules of heat is given off. Since it is given off, it is exothermic, so it must be negative. Very good. All right. I want you all to have a great day.